So we're going to look at a couple of examples of inclined planes. Like I said, we can really vary them and they can get really rich and complicated quickly. The main thing with them is always take your time, make sure you're drawing your free body diagrams. The FBDs are so important. So we have a 20 kilogram box. It sits atop a plane with an incline of 25 degrees. You know what I'm going to do actually? I'm going to change this to 25.0. Let's just make this nice and simple for SIG-DIG purposes. I should have done that before I presented this, but here we are. So we're going to say it's an incline of 25.0 degrees. So we're going to assume the plane's frictionless. We want to determine the magnitude of the acceleration of this box down the plane. Or what we're really asking for is the acceleration parallel to the plane. So the first thing is we want to draw a free body diagram for this situation. So my free body diagram, FG is still always going down. I'm going to have that normal force acting, well, normal or 90 degrees to the surface. So here's my FN. And at this point, we would say your free body diagram is complete, but I would always recommend for this stuff with free body diagrams, sketch out your components on the diagram. So we're going to sketch out FG perpendicular here, and then we'll sketch FG parallel here. Again, we always want to draw our components as dashed lines. Now, we also have to set a positive convention. Now, usually for us in the y direction, we'll call y up as positive, or at least up with respect to the plane. So we're going to call this y direction here that's perpendicular to the plane up. That's going to be positive. For the x direction, I would recommend, since this box is sliding down the plane, that is the direction of your net force parallel with the plane. Let's call this direction x down the plane. We're going to call that positive. So we've reoriented our coordinate system. The next thing to do is let's look at the net force. But we're only going to look at F net parallel to the plane. Because what we're interested in is we're interested in the acceleration parallel to the plane. So when I'm talking parallel to the plane, I'm only talking about looking at the forces that are literally parallel with the plane. And the only force that's going to be parallel to the plane is this FG perpendicular, or sorry, this FG parallel. So I can say that the net force parallel to this plane, this is going to be the perpendicular component of the force of gravity. I don't have any friction, nothing else to worry about, so I could say that the mass times the acceleration that's parallel to the plane, which is what we're looking for, this is going to be equal to mg times sine of theta. So again, FG parallel uses sine. Well, I have a mass term here and I have a mass term here. We can get rid of mass. And I'm going to get that the parallel component of the acceleration is just the acceleration due to gravity multiplied by sine of the angle. So that was nice and that was really convenient. We can calculate that. As always, just be really mindful, since we're using trig functions here, you want to make sure that your calculator is in degree mode. If it's in radians, you are not going to get the right answer and we will not be happy about that. So I'm going to get about 4.1459 meters per second squared. Now, since I'm going to present an answer, we'll deal with SIG-DIGs. So I'm going to say that the acceleration of this thing down the plane is about 4.15 meters per second squared. It just asked for the magnitude. We don't need a direction. If you were so inclined to put a direction, 4.15 meters per second squared down the plane works perfectly fine. Now, we got a box. Now, we're going to continue with this. So this box, it's going to start from rest, and it's going to slide a total distance of 30 meters down the plane. So what we want to do is we want to find the speed at the bottom of this plane. So we're not looking for velocity, we're just looking for speed. So what do we know? We know it starts from rest, so we know VI is 0. VF is what we're intending to find. We're told the distance it has to travel. It's 30 meters. And then we calculated the acceleration previously. So since we're looking parallel to the plane, we're looking at the parallel component of the acceleration. So I'm just going to write this unrounded value for our acceleration. So we need an equation that has VI, VF, D, and A. Well, the equation that's going to help us out here is going to be VF squared is equal to VI squared plus 2AD. And again, since we are starting from rest, VI is going to take a hike. We don't need that. So I get VF squared is 2AD. But this is really nice and convenient as well. We are solving for VF, and we have VF squared. So we're just going to square root both sides. So the final speed at the bottom of this plane is going to be 2AD. And the square root of that, sorry. So last bit, let's plug in what we know. So we know that VF is going to be twice times that acceleration that we calculated in part A and multiplied by that distance of 30 meters. Again, for this acceleration, use your unrounded value here. So if we calculate that, we're going to get about 15.8 meters per second. So we could say that the speed at the bottom of this plane is about 15.8 meters per second. So the box it's traveling at a decent speed, so we probably don't want to be standing in the way of that. But also realistically, we're not going to be dealing with frictionless surfaces. There's going to be friction involved.